So in this video, we're going to talk about the idea of the endothermic reaction versus exothermic reaction. And what really is being transferred is actually heat, which has a specific formula. Okay. And so if we have some sort of system and we have some sort of energy flow, okay, out into the surroundings, then we say the change in energy of the system is actually less than zero. So we should have a negative sign. And the change in energy of the surroundings obviously is becoming positive. So you can imagine the system is losing energy to the surroundings. So the surroundings is gaining energy, which means that obviously it's going to get the positive. It's going to be more positive, and the system is actually losing energy, so it's becoming more negative. And vice versa, if we have the system that we have energy flows into the system, then obviously the system is becoming more positive, and the surroundings obviously is losing energy. So hence the reason why it is less than zero, or it's going to gain that negative sign. Okay. No, and we just say that, and we just said it already. We just need to put it in terms of context. So if energy flows from the system, okay, the chemical reaction, obviously, to the surroundings, then we call this an exothermic reaction. So if energy is flowing from the system to the surroundings, we say it's exothermic. Now, vice versa, if energy is flowing from the surroundings into the system, then we'll call that endothermic. So in other words, we're putting energy into the system. Endo, that word endo, in. You should think of that as being inside. So if we're putting energy into the system, in this case, a chemical reaction, then we'll say that is endothermic. Okay, and so let's take a look at the graphs and the differences. Okay, so here we have the graphs of the endothermic and exothermic reactions, and we should see some striking difference here. Obviously, the y-axis, we have the change in energy, and then on the x-axis, we have the reaction progress. But notice for the exothermic reaction, the energy of the reactants are actually higher than the products, okay? So whenever you have the idea of the reactants being higher than the products, then we have an exothermic reaction, okay? In other words, the system is giving off heat, okay? And vice versa for the endothermic reaction, where we're putting in heat into the system, we're putting in energy into the system, energy of the reactants are going to be lower than the energy of the product. So those are the differences between the two graphs when we look at the graphs with these. Okay? And so what is happening with this is actually heat. Okay, and so we talk about energy Q, this idea of Q, we talk about the transfer of macroscopic, in this case we call it macroscopic work when we talk about physics. Okay, and so it's actually a transfer of heat. And so this beautiful formula says Q is equal to mc delta T, where CS subscript S stands for the specific heat and specific substance of interest. So this number will vary. If we're talking about water, then we'll see a different specific heat. If we're talking about copper, we'll see a different specific heat. If we're talking about aluminum, there's going to be a difference. So this number varies, and this number should be always given to you. Now the mass, obviously, that be always given to you. Now obviously you could solve for mass in different scenarios, but again, these are variables that are usually given. Okay, and then delta T, which is important, delta T is actually equal to the temperature, the final temperature minus the initial temperature. So that's something we need to be careful. Anytime we see delta in science, actually in science overall, anytime you see this idea of delta, it's always final minus initial. It's rarely any case that I've seen where it's initial minus final, but it's usually final minus initial. But again, remember that delta T in this case has to be T final minus T initial. Okay, with that being said, let's look at the problem. So this problem says, how much heat is absorbed by a piece of copper as it warms from -8 degrees Celsius to 37 degrees Celsius? Well, we know a formula. We know that Q is equal to mc delta T. Okay, in that case, we know the mass happens to be, it's given. So this is 3.1 grams. The specific heat is 0.385 joules per gram per degree Celsius. Okay, and we're going to simply multiply this by delta T, which is T final minus initial. So warms from -8 to, so this is our final. Okay, so if that is our final, then we say this is 37.0 degrees Celsius, and we're going to minus that, okay, minus 8 degrees Celsius. Okay, so notice that it's T final minus initial. Well, my initial happens to be negative, so we gotta be very careful here. So in this case, actually what we're doing is actually adding. Okay, and so if I add, I'll get if I multiply everything, I'll get approximately 53.7 joules. Okay, so this will be my heat. Now, just as a so this would be the answer. Now, so just as a tip here, usually they usually ask for these answers in kilojoules. Okay, the usual formula is kilojoules. So be very careful. Notice that because we're dividing temperature here, C is actually on the bottom here, and so you can see that my degrees Celsius and my degrees Celsius will actually cancel out. Grams is being divided here. Grams is being multiplied on the top here. So notice that grams and grams will cancel, which only give me joules. Okay, but again, if you want to get this in kilojoules, simply divide by 1,000. Okay, because we know that 1 kilojoules is equal to 1,000 joules. So if we divide by 1,000, we'll get the answer in kilojoules. But again, this is the tip. The answer is usually given in kilojoules. Okay. So let's take a look at another one. So how much heat in kilojoules must be absorbed by 15 grams of a sample of water to raise its temperature from 25 degrees Celsius to 55 degrees Celsius? Well, how much heat? Well, we know again, Q is equal to mCs delta T. Some people like to call this MCAT. I don't know why, but I guess I see why MCAT. And so Q, in this case, well, we know the mass happens to be 15.0 grams. We're going to multiply by the specific heat of water, which is given, which is 4.184 joules divided by grams per degree Celsius. Okay. And this is going to be multiplied by delta T. So temperature from 25 to 55. So notice that 55 is my final. Okay. So 55 is my final. 25 is my initial. So if I take 55 and I subtract that from 25, I should get around 30 degrees Celsius. Okay. And that's simple. Now plug this in. So if I multiply this out, this will give me approximately Q is going to be equal to 188.2 joules. And again, because it's usually given in kilojoules, I'm just going to convert it to kilojoules. So for every 1 kilojoule, there's 1,000 joules. So notice that joules and joules will cancel out to give me kilojoules. So essentially I'm dividing by 1,000, and this will be equal to 1.88 kilojoules. Okay. So Q is equal to mC delta T is a very important formula we need to remember. And the problems are pretty much straightforward.